So, we're going to be doing a bit of Unit 7 today. So let's just get into it. Where we left off, this is part of Unit something. I don't know. Point 4? I think point 4. This one will... Whatever. Page 8. Here's where we left off. We were talking about these different trials, and taking data from each trial about a certain reaction and seeing what K values we get. So plugging into that ratio, blah, 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 formula. Hopefully you were here for that part. And then once we're at this point, hopefully it's clear of what do you notice about your K values. And I want you probably should think for a moment, like, what does it mean that we're getting all these same values? But when we're talking about K, this is representing the ratio between products over reactants, right? At equilibrium, right? So at equilibrium, because we got the same K for everyone, no matter how much stuff you begin with, no matter what your starting conditions are, at equilibrium, K is going to be the same. It's like a property of your reaction. And we'll try to really hammer that, I will say this over and over again, but the only thing that is ever going to actually change your K is going to be temperature. So as long as you are running the same reaction at the same temperature, no matter how much stuff you start with, it's going to end up with the same ratio at the end. Your equilibrium is going to be at the same place. I'm gonna be blowing my nose a lot. I'm sorry. I just that's how it's gonna be. Okay. Anyway, so let's take a few more. I recommend try these next few problems on your own first. But here's how I would go about solving these. We know we are given this expression, this reaction, and so if I want to write an expression for Kc, I know that I take my concentration of my products, raise it to the power of the coefficient, so square that, over the concentration of my reactants. All right. And then it wants me to calculate the value of Kc, and so we're going to look at a graph, the data that we were given, and we're going to make sure that we take data at equilibrium. So reminder, when we're looking at a graph like this, the flattened off part, that's your equilibrium. So we use the concentrations at equilibrium and plug them into our K value. So let's see. C at equilibrium was 0.4 molar. A was 0.2 molar. And B is 0.3 molar. Plug it in a calculator, and you should get this. Cool. All right. So now we're given a reaction, and we're said that we're starting with 1 mole sample of that. So it's just reactants. You just shove some reactants in a flask and heat it up and hope that this reaction occurs. We know that the flask is that size, and we know the temperature is that. So, the first thing you want is calculating the pressure before equilibrium is established. What they mean by that, they mean at the beginning, because that's what we have data about right now. So let's think about just the beginning. So, how does one calculate the pressure of a gas, right? This is just one gas at this point before the reaction happens. And I know I have moles, and I know I have liters, and I know I have temperature. And so hopefully that rings a bell. We have enough information that we can use the ideal gas law. Okay, that many moles. This is your volume. Reminder that we use the R that has liters and ATM in it because we want liters and ATM to cancel out, or we want liters to cancel out and ATM to be what we're solving for. All right, so looking at that setup, moles goes away, Kelvin goes away, liters goes away. Plug it in a calculator, and you are going to get 1.22 ATM 3 significant figures. Cool. So that is your starting pressure, your pressure of bromine and chlorine. Cool. All right, cool. And then how would we get Kp? Or sorry, yeah. It just says KEQ, so technically you do in terms of concentration or pressure, but looking ahead, we know we have pressure, so let's do it in terms of pressure. Pressure of your product, pressure of your other product, over the pressure of your reactant. That's an R, obviously. Okay. And then take a second, read this next problem here. There's lots of ways of figuring this out. Honestly, some of you, this might be a little overkill for some of you. I'm going to write it out just kind of in words because for me, like to kind of organize my thoughts, this is just how I would set it up. If you don't like it, try it a different way. But I know that, okay, once equilibrium is established, I know that I have lost 42% of my BrCl. And then I want to figure out what KEQ is. So remember, if I want to use this expression, K is at equilibrium. So I need to know all of my equilibrium pressures, right? So I need to figure out all those so that I can plug them in this equation and solve for K. So let's think about that. So what I know here, I know that 42% of my reactant has decomposed. So let's use that and see if we can figure out, okay, well, how much do I have at equilibrium then? So here's how I would do that. I'd be like, I don't want to think about, okay, well, when I say 42% has decomposed, that means 42% of it has been used up. So this is how much has been used up. I know I started with that many ATMs, right? And I know I have used up 42% of it. So that's how much got used up. And then that means that this much must be remaining, right? My starting amount minus that much. So my pressure of my bromine monochloride at equilibrium is 0.71 atm. Okay, so we figured out our reactant pressure, partial pressure, but then we need to use this information to figure out the partial pressures of my products as well. So again, some of you guys might be able to just do that, or maybe see ahead, or you see a different solving strategy. Well, that's cool, do your thing if you want. Here's how I would kind of choose to organize my thoughts here. This is just a way of organizing our information about reactions. We're going to see another example at the end of this video of how we might set up problems like this. So this is just how I'm going to set up my information just to help me kind of logic my way through this. So let's see. Let's just kind of organize the information we know, right? Okay, so I know at the beginning there was some stuff, and then some change happened, right? Some stuff got used up, some stuff got produced, and then I know I reach an equilibrium at some point. So let's organize what we know here. I know I started with that and no products. And I know that I ended with this much of that. I want to figure out these ones. I'll just leave them blank for now. So let's kind of think through, and again, this might be overkill for some of you, but let's kind of think through what change actually occurred here. I know that I decomposed, this many ATMs of that starting material, right? And I wanted to think about, okay, well, how would that apply to how much product got made? So one way we could kind of represent the change mathematically, if we're looking at this reaction, right? Look at these coefficients we got. Every time the reaction happens, I use up 2 of these to make one of each of those, right? So any change that happens if I use up 2 moles of this thing, so let's just say X, 2 ATMs, remember moles and ATMs are proportional given our ideal gas law, so whatever. So you're going to use up 2 of that thing for every 1 of those you get to make, and every 1 of those you get to make. Hopefully we kind of see how that expression is going to be true based on the molar ratios. So if I know that 2x, right, if I know that, okay, oh, there we go. Okay, if I know that 2x is the same as 0.15, what is x? Divided by 2, right? I know that my x has to also be, or has to be this, right? Okay, plus. So I can know that my final equilibrium pressures of both of these, 0 plus 0.26 is 0.26. All right. Cool. So again, maybe you could have done that a different way, but that's how I would kind of organize my thoughts if I was not quite sure what to do with this problem. Cool. So now I know my equilibrium pressures. Those are what get to be plugged into our K expression. So let's go back to that. K pressure is equal to the partial pressure of the products, partial pressure of the reactants over the partial pressure of the reactant squared. Oh, squared. Neat. Okay, cool. So that's one way we might, some of the strategies we might use to get K. We'll see some others in a bit. Cool. So let's kind of reflect a little bit on when we get a K value, what does that actually mean? What can that tell us about where we are at our reaction and like a property of a reaction, right? So remember when we get K, it's products over reactants. So it's basically telling us the ratio of products over reactants. When you get to equilibrium, is your reaction going to be product favored or is it going to be reactant favored? Want to point out, because it's super common to get these mixed up, just because you have a K, just because you have big K or a little K, whatever, it does not tell you anything about the rates of the reaction, the forward rate versus the reverse rate, right? So it tells us about a property of when you're at equilibrium. It does not tell you how fast you get to equilibrium. Which can be confusing. I know there was lowercase q in the rates unit, and now there's lowercase k, and now there's uppercase k, and you're like, well, they're both k. Well, no. It's annoying. Super common multiple choice to try to get you tricked up on that. Keep them separate. There's nothing about how fast you get there, just about what the ratio is once you're at equilibrium. And like I mentioned earlier, the only thing that is going to actually change your K value is going to be temperature. As if every other, doesn't matter if you change your starting concentrations, doesn't matter if you change the size of your vessel, as long as you don't change temperature, K will be a constant. K is for constant. So let's just kind of think through for a second what it might tell us, what the size of our K value might tell us. So remember, K is this, right? So I bet you could do this on your own. But if we end up doing this expression, right? Taking our concentration of our products and taking the concentration of our reactants, and you end up getting a value that is greater than 1. All you math geniuses out there, the numerator must be the bigger thing, right? If you end up with a thing that is larger than 1. So if you get a K that is larger than 1, that is going to indicate to you that you have a reaction in which products are favored at equilibrium. Inversely, if we said, okay, well, I have products and I have reactants, and you get something that is less than 1, you must be dividing by a bigger number, right? So if you get something less than 1, that is indicating that you have a reaction that is reactants favored. Cool. And then, of course, what if you got 1, right? Exactly 1. The only way that would be true is if these numbers were exactly the same, right? And just to be clear, remember when we are looking at that expression, it's like the product of all the reactants, or sorry, all the products over all the reactants. So not necessarily that everyone has exactly the concentration, but the same concentration or whatever, but that the ratio, that the overall products matches the overall reactants. If you see an example, it might make more sense. But so this would mean that neither are favored. Your concentration of products and concentration reactants. It'd be more accurate to say the product of each of those, but whatever, are equal in equilibrium. So pretty rare. But if you have ones that it's perfectly in the middle, like you start with 1 mole of reactant and only half of it reacts, that kind of thing, this could be said to be true. All right, so take a second. I'm sure you guys could do this. Given these different reactions and this information about them, are they product favored or reactant favored? And hopefully you are able to tell me that this one is product favored, right? A big number. This one is reactant favored, this one is reactant favored, and this one is product favored. Do want to point out, some of you might notice, if K is like ridiculously large or ridiculously small, like this one, like times 10 to the 55. That's product favored, but it's like really product favored, right? It's like, like what that's telling you is like, there's like no reactants, right? So, it's not something that comes up that often, but if you see something like that, like you should be able to recognize like, oh, hey, like this is kind of like all the reactions we've talked about that are like irreversible, like all of the reactions that that you've seen so far that are like just a straight up arrow instead of the equilibrium arrows, right? This is like what their K would, because everything has a little bit of a reverse reactions. Irreversible reactions are kind of a lie, but like this is the kind of K that those type of reactions would have, right? Like it's practically all products. So if you see like a ridiculously large K, like there may be scenarios in which you can like kind of ignore all the equilibrium stuff. Like I'm going to teach you some math that we have to do to figure out like equilibrium concentrations and stuff. But if the K is like ridiculously large, you probably don't need to bother with all that. Like you could just treat it like a normal question, do your stoichiometry like we did in Unit 4, So it depends on the scenario, but do want to point that out to you. Conversely, if you have a ridiculously little K, that means that it's practically all reactants, right? So, again, it depends on the scenario, what they're asking you, but that basically doesn't happen, right? If you start with reactants and then it is still all reactants at equilibrium, the reaction is super unfavorable, doesn't really happen. So I can't think of an example in which they would want you to understand that, but I don't know. Sorry, not speaking very well. Yeah, you just recognize that, like, okay, that's not a very unfavorable reaction, like it's not making much product, if that happens to come up. Cool. Do want to remind you about K versus Q and how we can compare those two values. Okay, so reminder that Q, they're both the same equation, right? It's the ratio of your products over your reactants. But the difference is, if you do this equation, if you do it at any point that's not equilibrium, you call it a K. if you do that equation at equilibrium, then it is called K. So that's the only difference between those. So like if you could do this calculation at the beginning and see the ratio. Or like if you're given like some starting materials, you're given some of reactants and some of products, and you put them in a box together, and you would do this calculation, and that would be a Q value. You could see, oh, am I at this side of the reaction, or am I at that side of the reaction? And we can compare that to where equilibrium actually is. So when you get a value for K or a value for Q and you are trying to compare them, the comparison can help you understand how the reaction is going to shift in order to reach equilibrium. How will it shift in order to reach equilibrium? So is it going to need to do more forward reaction, make some products to get to that balanced place, or is it going to have to go reverse and make some reactants in order to get to that balanced spot? So, again, take some time to kind of think about this on your own, but what would it mean to have these different scenarios? You could have a K that is larger, you could have K and Q be equal. You could have a Q that is less than your K. You could have a Q that is greater than your K. So, again, you can memorize these, but I really encourage you to like pause and think about like what this means when you're doing this kind of problem solving, so that you keep all these things straight. Cool. So if you do this calculation and they're the same, right? That would indicate to you that P, the concentration of products, and the concentration of reactants are the same as what you would have at equilibrium, right? So that means that, oh, hey, I'm at equilibrium. We did it. So no shifting occurring. The rate of your forward reaction and rate of your reverse are equal. It's just going to sit at that point. But if you have a Q that is less than your K, right? If you do this little calculation, right? Products over reactions, and you have something that is smaller than K, you must be dividing by something bigger. You have more reactants, right? So if you have more reactants than what you would have at your balanced equilibrium, then the reaction is going to react to that. You are going to do forward reaction for the time being. So your reaction is going to shift to the products. All right, shift towards products, that's usually the phrase we would use. And what that means is that the forward reaction is going to be, like at that instant, the rate of the forward reaction is going to be greater than the rate of the reverse until they get to equilibrium and they can be even again. Conversely, if you have a bigger Q, that must mean that you have more products than what you would have at equilibrium. So how is the equilibrium reaction going to react to that? It's going to want to make more reactants to offset it, right? So your reverse reaction has to speed up a little bit. So that we can shift towards reactants. Sick. So yeah, kind of like that visual shows, like at equilibrium, K and Q are equal. And you're going to have to shift in order to get your Q to get to that ratio of K. Anyway, again, try these two examples, see if you can do it. Think about what information you're given here about your reaction. What does K tell you? A K that is less than 1, hopefully we now recognize, oh hey, you're dividing by a big number. You have a reactant favored reaction. So when we draw our diagram, the only thing that would have to be true is that you have more of the reactants than the products. So so if you were trying to draw that equilibrium, let's say I did 2 of each of my reactants and 1 of my product, that would, what I've drawn would be reflected by that, right? As long as you have more reactants at equilibrium, then that K value would be accurate. Cool. And then, cool, looking at this one. Hopefully we recognize that having a K value, the only information that we're given about that is the favorability of our products versus our reactants. Does not tell you anything about rate, right? Initial rate. It doesn't tell you how fast you get to equilibrium. And hopefully you recognize that, okay, well, it doesn't tell me anything about endothermic, exothermic, right? You would need some information about delta H, right? That is the value that tells us endothermic. So yeah, the more we learn, the more it is like just stuff to keep track of like, oh, if I'm giving this variable, what information can I get from that and what can I not get from that? So, you know, kind of a lot to keep track of. You might want to come up with some kind of strategy to start keeping track of all of these different values that you could be given. Neat. What are we doing now? All right. Okay, so one way that you could come up with K is getting values for your equilibrium pressures or concentrations and plugging them into the equation, right? That's one way. Another way is pretty similar to Hess's law. So let's take a look at this, and you know, again, try it on your own first maybe, but if I'm looking at my reaction, I could write an expression for Kp that would look like this. And when we've been writing our K expressions, right, we've been looking at it from the perspective of our forward reaction, right? The products are those ones, and the reactants are those ones, and the products get to go on the top. If I wanted to take and make a equilibrium constant expression for the reverse reaction, and you can write it out if you can't see it in your head, but like, then it's going the other way, right? So now these are my reactants, and these are my products. So my expression for K would look like this instead. Okay, so hopefully looking at those, you can recognize, okay, well, oh, sorry, I should have labeled this. This is reverse. Hopefully we can recognize, okay, well, if I wanted to have the reverse reaction K expression, it is just the first one flipped, right? So one way I could represent that is that this is the same as 1 over Kp, right? And hopefully we also know, I could also write that like this, right? So mathematically, if you flip around a reaction, the K expression will be the inverse of that of the forward reaction. Okay? And we are going to use this because, like with Hess's law, where you can get delta H from looking at the delta H's of each step or of the delta H of different reactions, we do the same thing with K. It looks almost the same, but it's slightly different, so it's hard to kind of keep track of. The difference is if you are combining different reactions and trying to combine their K values to get an overall K value, you have to take the product of all of those individual Ks. So I'll show you. Remember with Hess's law, we add them up. Now we're going to take the product. So like here, just a simple one where I don't have to do any manipulating. I don't know why my spacing got thrown off here, but whatever. Here you have a mechanism, right? Step 1, step 2, elementary steps, and then our overall. Prove it to yourself. That would cancel out, right? We're getting that overall that's written on the bottom. And so then if I wanted to know the Kc of this whole reaction, I could take that first K and multiply it by that second K, and that would get me what I want. Right? Okay. So that's just a thing we are able to do. like with Hess's law, we might need to manipulate our reactions in order to make them align with our overall. So like with Hess's law, and you need to adjust your delta H, if you manipulate your reaction, you also have to manipulate your K. But, think about what's represented with K. If you have to multiply a step by a factor, so if you have to double everything, if now you have coefficients of 2 on everything, think about what your K expression would have, all your stuff would be squared now, right? So if you do this, you have to raise your K value to the power of the multiple. Okay, and then we just kind of proved to ourselves, if you have to reverse a reaction, now your products are on the top, and they've switched, so you have it to the inverse of your K. So again, it's just slightly different from last time. It's not just switching of signs, it's about doing 1 over that K you originally had, not just multiplying, raising to the power. So take a second, look at this one. Try it on your own. How would we manipulate this system in order to get that overall reaction? I'll write it out for you in case we're having trouble seeing it, but hopefully with some more time you'd be able to recognize, oh, I gotta take this one, I gotta double it, and I have to flip it. So I'll just write it out just so we all see it. If I multiply by 2 and flipped it around, it would look like this. Sorry, 3. Okay, and I also have to mess with this one in order to get it so my HCl's all cancel out and I have 6 remaining. I need to actually multiply this by 12. So that instead this would be 6, 6, and 12. Okay, so when I flip this around, right, so now it looks like that. My K, I would have to inverse it, right? So 1 over, or raised to the negative power. And then I'd also have to square it because I doubled it. So my K1 is now going to be that. This one I multiplied by a factor, so I have to raise it to that power. I have to raise that to 12. So when I go to get my K of my overall, and again, you could go through and make sure these cross out and cancel the way that you want to. But they do. So the K expression for this, you'd have to multiply together the squared inverse of the first K and the second K, and then multiply that by the third K to the, I don't know what it's called when you raise it to the 12th power, but to the 12th power. Cool. So that would be your expression for that. Again, try this one on your own first, but with a little bit of staring at it, hopefully we recognize we got to take this one and we have to multiply it by 2. So then that means we have to take this and square it. And this one we're going to have to flip around. So this would get, it'd be 1 over K2 or raised to the negative 1. And so the only answer that reflects that, those two changes, is D. All right, so that's the only things, those are the two things I want you, or those are the units I want you to do practice problems on this weekend. We did get to talking about 7.7, so you have more time to kind of reflect on it and start to get it in your brain. This is the primary problem solving strategy we're going to be using this unit and next unit. I've teased these a little. I think they're a very helpful way of kind of setting up information about our reactions and understanding what changes occur over the course of a reaction. There's going to be several applications of this that might be helpful, but most of the time what's going to be is maybe you know some stuff about your reaction, right? You know K. You know how much the reaction happened. You know what the ratio is going to be at equilibrium. And you know what you started with. You know that you put some stuff in a flask, But then you want to know, okay, well, at equilibrium, at the end of my reaction, how much stuff do you have? How many reactants? How many products do you have? So that's usually what we're going to be using this for. So this is kind of, you've seen me set up problems kind of like this before. But what we're going to do, we're going to write a reaction, and then underneath it, we're going to organize the following information. We're going to make a row for initial concentrations or initial pressures. Yeah, I should probably clarify that. We can use these types of setups for several applications. Often it's going to be in terms of pressure or in terms of concentration. I'm going to also encourage us to sometimes just use moles, but you'll see a bunch of examples. Anyway, so you have one row that is your initial stuff, and then you have another row that's representing the change, so how much got used up, how much got produced, based on molar ratios, and then that last row will be representing what is your stuff at equilibrium. All right, so I already showed you one of these with this reaction, right? So let's write that out again. We have these reactants. Nope. There we go. Okay. And then let's organize our information underneath here. We want to make... Oh my god. Okay, I'm not stopping this recording. We're going to keep going. Please. Our fire alarms are super sensitive. They go off like if you make toast. So apologies. Anyway, let's make ourselves a nice table. So the way these are going to look, we're going to organize our initial information that we know. So I know I started with this much reactant and no product. So again, we can just put in, it's okay to use pressures or moles or concentrations in these tables. It's basically just about representing and organizing molar ratios and understanding what would change over the course of a reaction. So those would be my initial things. And then the change would be based on our molar ratios. So over the course of this reaction, I have to use up 2 of these, right? 1 of each, and I get to make 2 of those for every 1 BR2 and 1 Cl2 that I use. I get to make 2 of these. So the change over the course of reaction, every time I use up X amount of those, I get to make 2X amount of that, right? So my equilibrium, I could make an expression for what that pressure is going to be at equilibrium. It'd be that minus X, right? This minus X. And then 0 plus 2X. Just 2X for that one. Okay? So I could go and I could write my... sorry. I keep almost sneezing. Okay, anyway. The question actually asked me, what are the pressures at equilibrium after equilibrium has been established? So in order to know what the heck that is, I need to know what X is, right? So let's figure out what X is. And that's what I'm going to show you how to solve for that. So I do know that if I have all these pressures at equilibrium, they're going to be equal to Kp, right? So that's often what we're going to have to do. We're going to write our expression for Kp based on our reaction. All right, and now I know this value, right? And I know that that is going to be 2x, and this is going to be that minus x, and this is going to be this minus x. Okay, so we have to solve for x by setting these equal to each other, and then we can figure out what our new pressures are. So you're all good at math. I'm sure you could solve for these. You might be looking at this and be like, well, I'm just gonna multiply it all out, do some factoring, just multiply it all out, use the quadratic formula, solve for it. Don't bother. I mean, you totally could. That's a waste of your time, honestly. There's gonna be 2 different tricks that you're always allowed to do for this class. You're always gonna be given problems in which these tricks will work so that you don't have to bother doing the quadratic formula all the time. You could, but it's a waste of your time. Don't do it. So let me show you two things. I mean, I'm sure some of you guys might notice already one trick. Perhaps you notice that these are perfect squares. My numerator and my denominator are perfect squares. So that'll be the case sometimes. Hopefully that sounds familiar from factoring. I don't even know when you learned that in math. It has been too long. But what that means is that you have a thing in the numerator and in the denominator that are both squared. So like looking back at that expression we just wrote, right? We did k is equal to 2x squared over 1 minus x times 1 minus x. Looking at that denominator, hold on. We got, I'll plug in my value for k. Was it 5? I think so. 2x squared. And then hopefully we recognize, oh, well, this and this multiplied together, that's the same as it being squared, right? So I can just write this like that. Okay, so if you have things on the right-hand side that are both squared, we can go ahead and do a little square root action. That square root will apply to both my numerator and my denominator. And I just have to square my other side of the equation. So that'll get us this. Okay, and you can do a little distributing and multiplying and blah, 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 algebra, solve for x, and you would get this. Okay, so that's one solve strategy. So if you notice that they're perfect squares, go ahead, take some square roots, and that'll clear that up. But sometimes they're not perfect squares. So what is the trick to making these work and getting yourself out of setting up a quadratic? Some of you are not going to like this. I didn't like it. I don't like it either, but it's something we do. Okay, so I want you to take a second and think about, if we have a k that is very small, what does that mean? What does it mean to have a really small k? We know that means that it's mostly reactants, right? So there was a change, right? There's some products now. We used up some reactants. But compared to what you started with, there was minimal change, right? So what does that mean we get to do? We're gonna say when we're looking at an expression like this, where you took your initial thing and then there was a change to it, right? We're gonna assume that that x is so small compared to 1 or whatever your starting is. We're going to assume it's so small it's insignificant, it's negligible. Just to be clear, we're talking about like, times 10 to the negative 9-ish, or sorry, 4. I don't know, 9 looks like 4, I guess. So like 99% of the time, you are allowed to do this. So let's write our expression, right? Kp is equal to 2x squared over this minus x and this minus x. So what we're allowed to do, we're going to say that x is so small compared to 1 that it just goes away. Yep. And we can't get rid of the top one because, like, on its own, it's something. But in an expression like this where you're comparing it to a whole number, it's so small that we can just ignore it. So instead, you can just do this. Sorry, I keep forgetting my parentheses. All right. And then 2x squared is 4x squared, right? And then that's over 1. Divided by 1 is just the same number. So now this is equal to 4x squared. Algebra x is equal to 1.58 times 10 to the negative 3 ATM. Cool. So either strategy, both get you the same answer, right? Again, you will always be able to use one of these in this class. Never bother with a quadratic unless you really want to, I guess. Do want to point out with this left-hand side one, most, like, for this class, like 99% of the time we just do it and we're like, well, probably true. And we just do it, no problem. Technically, there is a way to, like, prove that this was a valid assumption to make. This is only, like, again, the assumption we're making is, like, the change was very small compared to our initial concentration. And by very small, it should be less than 5% of the original had gone away. Less than a 5% change. So if you want to check if this was a valid expression, when you go to college and you do, like, fancy, and you're, like, being a more thorough scientist than what you have to do to just take the test for this class, you should do these just to make sure that you are being thorough. For this class, don't bother unless they ask you to. But what we could do just to double check that this all works out, we can get a little calculation for our percent change over the course of our reaction. So comparing our x, remember that's our change in concentration, to our initial. Oh my god, I'm so sorry. Word. Although, plug that in a calculator, you get a very small percent change. I mean, hopefully you don't have to plug that in a calculator, it's just that. Right? So, less than 5% change. So, valid assumption. Again, don't bother unless they ask you to do that for this class. Okay, so all of that was just to figure out x, right? Like, if you even remember what the question was, we wanted to know what the pressures were at equilibrium, and we needed x, so we can plug them in there. So now that you have x, we can go through and plug it back in and solve for each one, find the equilibrium pressures of each thing. Right, so then we take our x and we plug it in for x, and then we solve for it. Yeah, I do want to I mean, in case anyone was wondering, like, you might be like, well, we assumed x doesn't matter, so the ending equilibrium is 1. No, we have it both ways for some reason. Yeah, so you make the assumption to solve for x, but then you still need to plug in x to solve for your equilibrium pressures. I mean, obviously it's going to be very close to 1, but do your due diligence. Show this anyway. Same thing for this one, right? And I didn't calculate this before starting this video, and I don't have my calculator next to me and don't feel like doing it, but I'm sure you guys can handle getting your last answer there. And that's how far we got in class. So again, you don't have to do the 0.7 practice quite yet, but now you know it, and you could, you know, start ruminating on it and start getting it in your brain over the weekend if you'd like. But yeah, that's that. Thanks for sticking with me on this candlelit video. Hope you like the ambiance. I didn't mean for it to be this dark, but anyway, have a good weekend. See ya. Just kidding. Okay, there we go. Bye.